I can live with that.
Great, excellent.
Great, so Dylan's going to do the introduction for this article by Shakun. Take it away. Okay. As he stated, my name is Dylan Peck, and I am presenting on the methods involved in the deglaciation of the Pleistocene. And as you all know, the article is by Shakun and all. Okay, so what I'm going to be talking about is why the Pleistocene Ice Age was important, why it was interesting for Shakun, and some of the methods they use, such as ice coring, radiocarbon dating, the GICC05 timescale, and proxy temperature analysis. Pleistocene is an amazing epoch is a time period, that was from 2.5 million years ago roughly to about 11.7 thousand years ago. And during this time there was major glaciations and deglaciations, and at any one point 30% of all landmass could be covered by glaciers. So this image depicts areas that would be covered by glaciers at this time, being in white, and the darker areas are not covered in glaciers. And this is really important for the Shakun article, because it talks about the northern hemisphere heating up much slower than the southern hemisphere. And greenhouse gases accounted for about 5 to 7 degrees change in temperature at this time, which is a great deal. So to emphasize what period we're in, I'm just showing the geologic time scale. And up here is the Pleistocene. It's a tiny little period that wasn't long ago. It's an important area, which, as you can see, in geologic time is not very far in the past. One of the methods they used was ice coring. Ice coring is an incredible tool for paleoclimate research. And what it is, it's basically the same way we core normally. You drill straight down into the glacier, and you get this cylindrical ice core. Why ice cores are amazing is they contain history of temperature at the time, sea level, volcanic activity, just a plethora of things. So they're very interesting, and I'll go into some depth as to what they involve. One of the other methods talked about was radiocarbon dating. As you all know from biology, geology, carbon is very abundant. And there are 3 main forms. There's carbon-12, which has 6 protons and 6 neutrons, giving it about a molecular weight of 12, hence carbon-12. And that composes 98.9% of all carbon found. It's a pretty big number. But the one that we're interested in for radiocarbon dating is carbon-14. Carbon-14 has 6 protons and 8 neutrons. They only compose about 0.1% of all carbon found. How carbon-14 is created and found is through neutron bombardment of nitrogen in the atmosphere. So neutrons hit this nitrogen and breaks apart into carbon-14, a radioactive isotope. Why carbon-14 is interesting is we can measure the half-life of carbon-14 to provide dates for sediments, what have you. I'm going into a little bit more detail. So carbon-14 has an expected half-life of about 5,730 years. What that means is if you had a solid block of carbon-14, in 5,730 years, half of that would decay to a more stable state, which in this case would be nitrogen-14. And if you waited another 5,730 years, there would only be 25% carbon-14 remaining, and the other 75% would be nitrogen. So carbon-14 decays in what is called a beta decay, which means an electron breaks off and becomes nitrogen-14. So as an unstable isotope, it's trying to reach a more stable state. However, one of the limiting factors of using carbon-14 as an age dating tool is you can only reliably go back about 50,000 years, which might sound like a lot, but thinking about the Pleistocene as being about 2.5 million years, it doesn't give very accurate data at such high dates. There are some methods that allow it to go back as far as 100,000 years, but at that point it's some 0.0001% carbon-14 remaining, so it's very small amounts. Not very hard to trace, and that explains a lot of the errors that they talk about in the paper. One of the other things that they talk about is the GICC05 timescale. They related they modeled their age data based on the GICC 05 timescale. And what the GICC 05 timescale was, or is the Greenland Ice Core Chronology 2005 timescale. And what that is, in 2005, 3 cores were taken in Greenland, these 3, and they gave a very good depiction of the oxygen isotope concentrations during this period. And oxygen isotopes are essential to describe what periods were glacial forming and what periods were deglaciating. Oxygen isotope ratios. So based on the Greenland cores, there are 2 major stable oxygen isotopes that we concern ourselves with, and that's O16 and O18. O18 has more neutrons than O16 and thus has a higher molecular weight. What this means in the world of paleoclimate is during periods, so when water evaporates, O16 is actually preferentially evaporated more often than O18 because of that minute difference in mass. And so it is carried over and it precipitates out. And so what this means during periods of glaciation is so more O16 is being taken out of the water, it's going over land, it's precipitating, and then that's freezing. So during periods of glaciation, there is a higher abundance of O16 found in glaciers with a higher concentration of O18 found in bodies of water. And so these ratios allow for more accurate depictions of when glaciers formed and when we had ice ages, etc. Proxy temperatures. So one of the main things they talk about in the paper is how they compared the ice cores in Antarctica to the proxy temperature data from around the world. And the main method they used to discover proxy temperature data was the study of alkanones. I didn't know what alkanones was, so I decided to focus on it a little bit. So alkanones are these ketones right here, very interesting long carbon chains with the double bond O group at the end. And why these are important is marine planktonic organisms, certain ones, create these alkanones. And these can be found in the sedimentological record. And why these are important is they measure the surficial water temperatures at the time. So if it's colder water, the planktonic organisms are going to make alkanones with more double bonds, while in warmer surficial temperatures, the planktonic organisms will make alkanones with less double bonds. As you can see, this one only has 2 and these have 4. So by studying the alkanones in the sedimentology record, you can actually see periods where the surficial temperature was warmer compared to colder. And that's actually what they used to map the global temperatures to compare against the Antarctic research. Their references.
Hello. Thunderous applause. Thank you very much. That was great. Let's pepper him and others with questions afterwards, if that's okay with you.
Yeah.
Anybody have any burning questions? Great. Thanks, Dylan. Go for it. Yeah. Why don't you allow that? That'll excellent. It doesn't.
They'll go.
Yeah, excellent. Great. Got it.
My name is
Clements is going to talk about the paper.
Yes. I'm going to talk about the paper by Shakun, global warming preceded by increasing carbon dioxide concentration during the last deglaciation. So a little bit about what I'm going to talk about today is paper, where they got their data from, kind of the setting of the world that they were looking at around the data that was taking place, purpose of the paper, a lot of the results that they came up with, their conclusions, as well as their sources of error coming at the end. So their data largely came from 80 core sites that were taken from all over the world, including some ice cores in Antarctica and Greenland. as well as cores from the deep ocean as well as on the land surface from all over the world to kind of give an average idea of what the world looked like at the time. So coming out first, the global proxy temperature stack, which is the proxy that he was talking about with that aging, is this blue line here. And as we see, over the several thousand years that this study is taking place, we see a warming trend, slight cooling trend, warming trend again. The Antarctic ice core record, which is the red line, they looked at separately because they noticed there was a slight difference in between the northern and some southern hemispheres. As you can see, the Antarctic ice core record shows that the Antarctica warmed faster or sooner than the global average. And so, as you can see with the yellow dots, which are the atmospheric CO2 concentrations, that line kind of remains pretty consistent with that, though they wanted to take a closer look. And again, as well, they looked at the histogram of where the data took place and the temperatures that were coming out of it. And the global average, as you can see, kind of is on the right-hand side of this dashed line kind of represents the major changes in CO2 concentration. The gray bars represent the global average, showing that it kind of comes similarly after the change in CO2s, as well as the northern hemisphere, which shows even more lagging behind the CO2, which just means that it came after the CO2 change. Whereas the southern hemisphere shows a lot of changes in temperature before there was any amount of CO2 change, before there was high amounts of CO2 change. So the purpose of the paper then is to try and find a correlation between the global temperature, is it tracking as closely with the CO2 as we think, as well as looking at the Atlantic meridional overturning circulation, which is just the southern ocean circulation that moves a lot of water around the South Atlantic, seeing if that would have caused heat to move around the hemispheres differently in the north and the south. So looking at the first chart, I really hated these figures because they were looking like this. They had so many lines on them, very confusing to look at, so I tried to break them apart and try and get a better look at what each one is. So the diamonds are the relative sea level at the time, and I matched that with the green line, which is the percent of the northern hemisphere that was covered with ice. As you can see, as more ice melted, sea level went up. It makes a lot of sense. And with that, the ice sheet, they talked a lot about albedo, which is the reflectivity of the Earth's surface. And obviously ice would have higher reflectivity than the land surface. So it would make sense that as we lose more ice, the land would be able to absorb the heat more coming from the sun. Moving on to the CO2 concentration, which are these yellow circles, and the global proxy temperature stack, which is that same line as before. As you see, it seems to be very well correlated. As the CO2 goes up, northern hemisphere or global temperatures warm up. There's a slight pause in increase in CO2, which actually is noted by a small decrease in global temperature, and then it goes back up into another plateau later on. Then looking at model global temperature stack, which is taking they took data from different. It's the same 80 core sites, but they looked at them a little bit differently and kind of traced in different ideas about what was driving that global temperature. As in the CO2, looked at mainly the CO2 concentrations, all kind of took everything into effect, things like that. So as you can see, the all line has warming, and it kind of wavers a little bit, keeps going up, as well as CO2, which kind of looks at the CO2 concentration goes up at pretty much the same rate. Guessing that maybe there's probably a correlation between the CO2 and the global temperature. The orb model stack, by contrast, shows the minor warming, not very much change, which kind of was consistent with a modest role in CO2 and more of the way the Earth is orbiting. Again, here's the same CO2 concentration. But then this time they split it up into the northern and southern hemisphere to see what the differences were. And this northern hemisphere, the blue line, is similar to what we saw before, where as CO2 comes up, you can see the warming, cooling, and warming again. However, the southern hemisphere, which is the red line, is shown to warm faster than the northern hemisphere. and even started warming before there was rise in CO2. And there's a slight pause here, but not as much as the cooling in the northern hemisphere. So the southern hemisphere continued to warm, regardless of what the northern hemisphere was doing, and was even doing it before there should have been CO2 that was affecting that temperature rise. Again, this is going away from the proxy in which it was modeled. It's a similar idea. We have the northern hemisphere, which is the blue line, and the southern hemisphere, which is the red, showing that it warms up sooner than the northern hemisphere. But they do end up at about the same magnitude at the end of the time period that we're looking at. And so this is saying that the southern hemisphere led the northern hemisphere in the warming in that area. So then we look at temperature differences in between the two. Northern hemisphere minus the southern hemisphere is the dark purple line up top. And this is mainly showing that there was a strict oscillation between warming and cooling of the Earth in multiple diagrams, including the North Atlantic. Everything seems to move in that similar pattern except for the CO2 model, which leads to believe that these changes were largely done by some other aspect, and they went with the AMOC current that was moving a lot of water around the southern hemisphere that led to more of the differences in temperature. So again, this is that AMOC strength, which is the southern Atlantic current, and these are just modeling how much of an effect the current had on the atmosphere. And as you see, the CO2 doesn't really take much effect, or doesn't take an effect almost at all. But this one really shows a great deal of impact on what the current was doing to the temperature. So putting all of that kind of together, they looked at the proxy temperature stacks, but divided up into 30-degree levels across the Earth. And you see, this is the seesaw, which is that oscillation before that we saw. But the southern hemisphere's areas tended to warmer much sooner, in the range of several thousand years before the northern hemisphere did, as it went up and down. But there was a substantial temperature change at all latitudes, reaching the same magnitude. And there's that small cooling in the northern hemisphere. And so they predicted this, but it's saying that the Antarctic was largely driven by ocean currents, just the way that our Earth was going, but that also led to an increase of CO2, which then helped warm the northern hemisphere. So, concluding with that, they stated that global temperature stack and transient modeling, which is all the temperatures that we look at, point to CO2 as a key mechanism for global warming, but that inter-hemispheric seesaw, which is the kind of differences between the northern and southern hemisphere, was directly related to the AMOC current variability as that current changed, and that Antarctica would have warmed up due to other processes than just CO2, but then that aided into pushing CO2 being the large driver of warming in the northern hemisphere. In the northern to high latitudes, the first warming of the last glacial maximum initiated the reduction in the AMOC that may have ultimately caused the increase in CO2. So the northern, would basically concluding that the northern hemisphere would have been warmer at some point, and that would have aided into the pushing of the AMOC current that then led to this deglaciation cycle. So this would error and date interpretation. They talked a little bit about some errors that they had, including the radiocarbon dating, which really, as he stated, works only to about 50,000 years, not the several million years that we're looking at here. They also talked about some of the data that they took was, it was interpreted by other scientists, and the chronological errors in the simulations that came up with the cores, they tried to play with that a little bit, but in the end, they didn't account for any errors that were always happening amongst the core data and the way the time was going. And any temperature anomalies they kind of threw out as being not useful for this study. So, thank you. Are there any immediate questions?
Hello. Thank you. Good job. Yeah, that was great.